Factors of a number are all the smaller whole numbers, they're going to be smaller numbers, that divide the number evenly with no remainder. And that's the important part here. So all the factors of 24, well, we're looking at smaller whole numbers, and the whole numbers start at 0. 0 we're not going to include though, because anything divided by 0 is undefined in mathematics, so that doesn't work. But 1, however, 1 can always divide a number. So the factors of 24 are going to be 1, and the next number, right, it would be 2. Well, can 2 divide 24? 24 divided by 2 is 12. So yes, it's a factor. 3 can divide 24. 24 divided by 3 is 8. 4 divided by 20, or 24 divided by 4 is 6. So 4 can go in there. 24 divided by 5, however, gives you a part of a whole number, right? 5 cannot go evenly into 24. So 5 is not a factor. 6 can go into 24. 24 divided by 6 is 4. And here we can stop because I found the switching point, 4 times 6. That means after this, 3 times 8 goes into 20, or 3 times 8 is 24. 2 times 12 is 24, and 1 times 24 is 24. So once you find this number where you have the pair, then you can just find the rest of the pairs, because they're always going to come in pairs. That's how factors work. Okay, for 18, of course, 1 can divide into that. 2 can divide in there, 2 times 9. 3 times 6. 4 cannot go into 18. 5 cannot go into 18. And 6 can, right? 6 times 3. So that's the breaking point there. 2 times 9, and then 1 times 18. And these are all of the factors of 18. A prime number is a number, is a whole number, but not including 0 or 1. The first prime number is going to be 2. And prime numbers have only itself and 1 as factors. So of course 24 and 18 are not prime numbers because they have many factors besides just 1 and 24, 1 and 18. These types of numbers that are not prime numbers are composite numbers. So it's just pretty much any number that's not prime, that's greater than 1 for the whole numbers. 0 and 1 we do not consider for prime and composites. So we can use this algorithm, the sieve of Eratosthenes. It's kind of hard to say, but to find the prime numbers, we always start with 2, right? Because 1 can't be a prime number. 2, therefore, the only numbers that give you 2, the factors of 2, is 1 times 2. Well, prime number says the only factors is 1 in itself, 1 times 2, so 2 has to be the first prime number. And the process goes like this. We're going to look at the multiples of the prime number we are looking at, which is 2. The multiples of 2 is going to be 2 times 1 is 2, of course, then 4, then 6, then 8, then 10, then 12, 14, 16, 18, and so on and so forth. And we're going to cross those multiples off on the chart, because these cannot be prime numbers, since 2 times 2 is 4. Therefore, 4 has a factor of 2. 6 times 6 is 2 times 3. So 6 cannot be prime. 8 is 2 times 4. It cannot be prime. 10 is 2 times 5. So it can't be prime. And so on. So all those happen. So of course we're going to get 12, 14, 16, 18, 20. And hopefully you can see the pattern here. It's really going to be all of these numbers in this column, in this column, in this column, this one, and this one here. So the next number in this list, 3, this must be a prime number because we've already considered all of the smaller numbers. So find the multiples of the next prime. It's going to be 3. We get 3, of course, then 6, then 9, 12, 15, 18, 21, 24, and continuing. So 6 is already crossed off. Don't have to worry about that one. But 9 is the next one. Then 12 is already crossed off. 15, 18, 21, 27 will be the next one. And let me go ahead and cross off the rest of them. And there we go. I've crossed off all of the multiples of 3. So now we can see the next prime number is going to be 5. Multiples of 5 is going to be 5, 10, 15, 20, 25, 30, 35, 40. 45 has been crossed off. 50, 55, 60, 65, 70, 75, 80, 85, 90, 95, and 100. 7 is the next one. 7 times 2 is 14, times 3 is 21, then 28. 35 is crossed off. 42, 49, 56, be 63, 70, 77. Let's see, 84, 91, 98, and then that's it. Now we're talking about 11, 22, 33, 44, 55, 66. Those have already been crossed off. 13. And I'm just going to finish the process off here. I'm just going to do the same exact thing I've been doing, right? 13 times 2 is 26, and then 39, and keep going on that. I'll cross off the rest of them. So as you can see here, I have found all the prime numbers. There are 25 of them, and I have them all circled here in red. And this is the process that you can use. You can continue this process, right, for any bigger numbers, but it becomes exceedingly more and more difficult. And this technique works for smaller ones, but for larger ones, you can just go ahead and, you use a search engine and look up, is a number prime, or look up prime numbers. They're known to very, very large numbers. Now, by the fundamental theorem of arithmetic, every whole number that's 2 or greater can be written as a unique, and I want to emphasize this word, unique, product of prime numbers. This is called the prime factorization. So primes, of course, are their own factored form because a prime number times 1 is the number itself. It doesn't need to be written any other way. So to find the prime factorization, there's a couple ways you can do it. Well, there's probably many different ways, but I'll show you 2 different ways to think about it. One of them that I like to use is the factoring tree, because this lets you use any 2 numbers that you can think of. So 72 is what 2 numbers multiplying together. It doesn't matter what 2 numbers you choose any 2 numbers. I can think of 8 times 9 is 72. 8 and 9 are not prime numbers. You can see that here, that neither of them are circled on this diagram. So I want to keep going with these. 8 is the same thing as 2 times 4. And here, 2 is a prime number, right? 2 was the first prime number that we had. So I'm going to box in 2. 4 is the same thing as 2 times 2, and those are both prime numbers. 9 is the same thing as 3 times 3, and those are both prime numbers. You can check that diagram again. See that 3 is the second prime number in the list. So what I have here is the prime factorization of 72. It's going to be 2 times 2 times 2 times 3 times 3. And that's the unique form, right? No other combination of 2 and 3 in this exact one with 3 2s and 2 3s. It will not give you any other number besides 72, which makes sense, right? If you always multiply 2 and 3, 2 times 2 times 2 times 3 times 3, no matter what order you do it in, you always get 72 as a result. That's the prime factorization of 72. This is called the factor tree method, where you just break it down into different branches, or the roots of the tree, if you want to think of it that way. Now, another way of doing this is taking a number and then dividing it by successively bigger primes until it can't be divided any further. So 600 can be divided by 2. That's the first prime number it can be divided by. That gives us 300. This number can be divided by 2 again, though. That gives us 150. This again can be divided by 2, giving us 75. And then 75 can be divided by 3, the next smallest prime, 75 divided by 3 is 25. This cannot be divided by 3, so I'm going to divide it by 5, which gives me 5, and 5 divided by 5 is 1. Once you have 1 here, that's when we stop. The prime factorization is on this side, on this column here. So 600 is the same thing as 2 times 2 times 2 times 3 times 5 times 5. Out of these two methods, I think this second way is a nice way because it gives you always a pattern that you can follow. However, it's not necessarily obvious what prime number goes in there. You can, of course, just check it, right? You can check 2, then check 3, then check 5, and of course check 7, then 11, then 13, 17, 19. But that has to, you have to keep checking numbers. Whereas the factorization tree that I've shown here, this is nice because you're just breaking down the number into whatever numbers multiply up into it. They don't have to be prime numbers, as I showed here. So let's try that again, the factorization tree on 270. No matter which way you do this, of course, you're going to get the same factorization. There's only one factorization that you can get. It's unique. That's what I was saying here. 270 is the same thing as 27 times 10. 27 is 3 times 9, and 9 is 3 times 3. 10 is 2 and 5, and there's my factorization. 3 times 3 times 3 times 2 times 5, or from lowest to highest, 2 times 3 times 3 times 3 times 5. That's the prime factorization of 270. Now, understanding what two numbers multiply to give you the factors or the prime factorization, divisibility rules can help. You can, of course, just divide it on a calculator. If you get a whole number as an answer, then you're good to go. If you have a decimal, then it cannot divide it. The main ones I want you to note here is going to be 2, 5, and 10. These are the easiest to see just by looking at the number. Any even number can be divided by 2, and even numbers end with 0, 2, 4, 6, or 8. If it's not even, it's odd. Odd numbers end in 1, 3, 5, 7, and 9. So 56 can be divided by 2 because it ends in 6, which is one of those numbers. 102 can be divided by 2, it ends in 2. 744 is even. 640 is even. But these numbers, these are all odd and therefore cannot be divided evenly by 2. Now, 5, it ends in either 0 or 5. So 85, this ends in a 5. 900 ends in a 0. And 1725 ends in a 5. Of course, 900 ends in a 0, so it can not only be divided by 5, but also by 2. And finally, 10 ends in 0. So of course, these numbers end in 0. Oh, this one is 1,000, million, billion. This one's 1 billion, of course, ends in a 0. So it can be divided by 10. There are, of course, divisibility rules for the rest of them. I recommend you read them up. 3, 6, 9, 8. 8's not too hard. 4 isn't too hard either. 8 and 4. But 3, 6, and 9 are fairly simple, but not as simple as 2, 5, and 10. Those are just the very easiest ones. It is important to note here that 6 is 2 times 3, which means if you can divide it by 2 and you can divide it by 3, you can divide it by 6. The same process works for some of these larger numbers, right? 12 is 3 and 4. 3 times 4 is 12, 3 and 4. If those two things work, then the number can be divided by 12. I kind of showed that here. 7 is kind of displays the, sometimes it's just not easy to know the rule. There is a rule for 7, but a calculator can easily just check if it's divisible by 7. So 2, 5, and 10, though, are very easy. It's easier to see that they're divisible by 2, 5, and 10 than it is by plugging it into a calculator. So I recommend you memorize those. All right. Here we want to list out the factors of each number, indicate if they're composite or prime, and then write the prime factorization. So the factors of 12 is going to be 1, 2, 3 can divide 12. 3 times 4 is 12. So it's going to be 2 times 6 and 1 times 12. These are the only factors of 12. Of course, this is a composite number. A prime number only has factors of 1 and itself. This one has more than that. So it is a composite number. And the prime factorization of 12 is going to be, we can use any one of these things. Let's use 3 times 4. 3 is prime, and 4 is 2 times 2. So the prime factorization is 2 times 2 times 3. Okay, 23, the factors of 23, of course, 1 and 23, 2 cannot go into there, it's not even. 3 cannot go into there if you divide that by 3. In fact, if you keep going up, you'll see that nothing else can be divided by, can be divided evenly. In fact, if you go back to that that tree that we see there, 23 is a prime number. So we already know that 23 cannot be divided by anything else. This is going to be prime, and the prime factorization of this number is 23 because it is itself a prime number. All right, 62. 62 has 1, 2 can go into there, 2 times, let's say 2 times 31. And I believe 31 was prime. Let's just double check there. Yep, 31's right here. 31's a prime number, which means it cannot be divided any further. 2 times 31, and that means 62 is the only other factor. I know this because if I break 62 up into 31 and 2, both of these are prime numbers. Those are the only two numbers we can choose. Over here, I could have broken 12 up into 6 and 2. 2 is prime. 6 is 2 and 3. Because there is a number that's not prime in this listing, that means there's multiple ways I can break this thing up into. This one, however, can only be broken up into 31 and 2. So I know there's no other factors. The prime factorization of 62 is 2 times 31. Okay, 28. Let's use the different factorization tree. This is definitely not prime, right? It's 2 can go into 28. Let's use this method here. 28 divided by 2 is 14. Can divide by 2 again. That's going to be 7. And 7 can go into 7, 1. So there we go. 2 times 2 times 7. This is definitely a composite number. And the prime factorization of this is 2 times 2 times 7. This was, of course, a composite number as well because we had factors other than 1 and itself. Okay, 144, this is an even number, so it's definitely not prime. It's going to be composite. Factors of this thing, I should do that first before doing the prime factorization. 144, we go 1 times 144, 2 times, it's going to be 72. 3 can go into there. The divisibility rule for 3 is add them all up. 1 plus 4 is 5, plus 4 is 9. 3 can go into 9, so 3 can go into 144. Let's see, can 4 go into there? Yes. 2 can go into there, which gives us 72, and 2 can divide 72, so that means 4 can divide 144. 5 cannot. Can 6? Yes, because 2 and 3 can go into there, so 6 can go into there. Can 7? No. Using that on a calculator, you can just check that. 144 divided by 7, let's see, gives us 20.57 and then some other decimals. So no, it definitely can't go into there. Can 8? I believe 8 can. I can just check that really quick. Divided by 8 gives us 18, definitely. The next one would be 9. I believe 9 can go into there. Just divide by 9. Yeah, it gives us 16. 10 cannot go into there. 11 cannot. If we check that on the calculator, definitely not. and then 12 can go into there. And then at this point, because 12 times 12 is its own pair, 12 times 12 is 144. So all I have to do at this point is just go back. I'm going to get divided by 9 is 16, divided by 8 is 18, right? 9, 16, 8, and 18. Divided by 6 is going to be 24. Divided by 4 is 36. Divided by 3 is 48. 2 is 72. And of course, 1 is 144. So those are all the factors of 144. There's quite a lot of them. Now let's find the prime factorization of this. 144 is 12 times 12. Both the 12s are 3 times 4 or 6 times 2, same thing. 4 is 2 times 2, and a 6 is 2 times 3. So 144 equals, let's say I've got 4 2s and 2 3s. That's the prime factorization of 144. Okay, 81's an interesting number. 81, the factors of 81 is going to be 1, 3, 9, 27, and 81. 9 times 9, 3 times 27, and 1 times 81. I know that because I actually know the prime factorization of 81. This is definitely a composite number because it's got more factors than just 181, right? It's not prime, so 81 is 9 times 9. It's a perfect square. And 9 is 3 times 3. 81 is 3 times 3. So actually, 81 is just 3 times 3 times 3 times 3. So these are the only numbers that if you multiply different pairs of them, you're going to get these ones. 3 times 3 is 9. 3 times 3 times 3 is 27. And of course, all of them together give you 81. Okay, 71, I suspect this is prime. Let's go back and check. And there it is, right there. So yes, 71 is prime. The factors, of course, of a prime number is just going to be 1 and 71. It is prime. And the prime factorization of a prime number is just 71.